Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Today we'll be talking about statistical formulation of the mechanical problem. This lecture is from the lecture series regarding the course of statistical mechanics, having the course code of PHY231. This lecture basically describes the 4 different steps for treating any statistical systems. This lecture is closely related with the previous lecture where we had discussed 4 different steps for the statistical description of a systems. Here in this lecture we will discuss the 4 step again, but we will solve some problem on that will be from physics, and we will apply the 4 steps of statistical description and calculate their final probability. And that is actually the basic objective of today's lectures. What we have specified the first step was to understand the specification of the systems, or to describe the microstates of any particular systems. The second steps among the 4 steps was regarding the statistical ensembles. We need to know the nature of particles and the property of the particles involved in that systems. The third step was regarding the postulate of probability, and that said that all the possible states are equally probable to each other, and that was the third step. And finally, the last step was to calculate the probability, and that was actually the calculation for the probability. So in today's lecture we will basically discuss some problems, and then we will apply these 4 steps on that, and finally we will calculate the probability. So the first thing is the specification of the systems, that is the microstates, and we need to consider any system of particles. We know that the particles will obey the laws of quantum mechanics. I'll discuss the classical description shortly, and we'll emphasize the quantum treatment of the particles. So for that we need to consider any system of particle, and using the quantum treatment consider systems with f degree of freedom, and it could be described by many particle systems, just like wave functions, and the wave function have f q1 q2 up to kf is the set of f generalized coordinates required to characterize the systems that need to be the position coordinate of that particles, or the position coordinate of that particular systems. For a system with f degrees of freedoms, the many particle wave function is formally written as psi into q1 q2 qf after t. So this is actually q1 q2 up till qf is a set of f generalized coordinates which are required to characterize the systems. A particular quantum state, that is the macro state of that system, is specified by giving values of some set of f quantum numbers. So if you specify psi at a given time t, we can in principle calculate this at any later time by solving the appropriate Schrodinger equation for that. So we need to briefly look at some simple examples which might also review some elementary quantum mechanics, and from that we can easily understand how we can apply the 4 steps on any statistical systems, and how we can describe that system statistically. So the very simple example is very simple, just like we have a coin that have 2 faces. I already discussed it before. So this is actually a single particle fixed in position, and we have intrinsic spin for that. The value of spin is equal to 1/2. Intrinsic angular momentum is 1/2 h cut. So in the quantum description of these systems, the state of the particle is specified by specifying the projection of m of this spin along a fixed axis, which we usually consider as a z-axis. So there are 2 values for that. The quantum number n can have this 2 value. One is the 1/2 value that is considered to be spin up, and the other is minus 1/2 value that is considered to be spin down. So there are 2 possible states for that. So if we apply the law of postulate of probability, so the microstates is 2, the possibilities are 2, and if we calculate their probability is very easy. We can do it by 1 over 2, because we have two phases, the total probability is 1, so 1 divided by 2 will lead to the probability of each arrangement of the particle. Just like for spin up, its probability is 50%, similarly for spin down, its probability is 50%. So we have two possible states for this particular system. Now coming toward the second problem, where we need to consider n particle, that is actually non-interacting particles, and that is fixed in position. Each has intrinsic spin of 1 over 2, so each particle quantum number mi, that is mi is equal to 1 to 3 up to n, can have one of the two values, that is plus minus 1 over 2, and we need to suppose that n is a huge and the value of n is around 10 to the power 24. So the state of this system is then specified by specifying the value of each of the quantum numbers, that is m1, m2 up till mn. So there are 2 key power n unique states of this system with n is equal to 24 is possible. So this number is quite huge and the things become a bit complicated, where we need to consider all the possible state for that. But this is the simple way how we can treat that systems. Let's come to this third problem, where we consider 3 particles. The value of n, or the number of particles in this particular case, is equal to 3, and these particles are fixed in position, each of the particle has a spin of 1 over 2. So each spin is either up or down. So the value of m2 for up is m is equal to 1 over 2, and value of m for spin down is equal to m is equal to minus 1 over 2. So each particle has a vector magnetic moment that is called mu. So the projection of mu along a z-axis is either a spin is either mu z is equal to mu for spin up, and our mu z is equal to minus mu for spin down. So it has two values. One is for spin up, another is for spin down. So this is the possible arrangement of the particles. So if we look toward the possible microstate for this particular case, so we can use the formula of 2 to the power n. So there are 8 possible arrangement that is possible for that. So these 8 possible arrangements are, each of them is considered to be a simple a separate microstates. So if we calculate the probability of any individual microstate, so that will be equal to 1 over 8 for that particular case. Here in this column is the total magnetic moment is calculated, that is actually the sum of the individual magnetic moment. In this case is all is added up, so it will lead to 3 mu. In some cases the two cancel with each other, leaving behind a single mu, and in this case 2 of them are minus and 1 is positive, so 2 cancel with each other and we have a net value of minus mu. And in this case all are spin down, so the total magnetic moment is equal to minus 3 mu. If we look toward the total energy of this system, so it has minus 3 mu h in this particular case, and in other cases we have, other 3 cases we have minus mu h, and in 3 other cases we have mu h, and finally at the other arrangement we have the value of energy that is equal to 3 mu h. So given that we know no other information about this system, all we can say is about it has equal probability of being found in any one of these 8 possible states. So what we do, put this system into external magnetic field H. So the classical description tells us that a particle with a magnetic moment mu in an external magnetic field has the energy is equal to minus mu dot h. If we can also write as a minus mu h cos theta, and theta is actually the angle between mu magnetic moment and the external magnetic field, that is h. So combine this with the quantum mechanical results. So this tells us that each particle has 2 possible energies. For the positive or for the spin up, the energy value is equal to minus mu h, because theta is equal to 0 in this particular case. And for spin down we have mu h, because theta in this particular case is equal to 180 degree, that is equal to -1, and that will cancel, the minus will cancel with each other. Then the value of energy in this particular case will be equal to mu h for spin down. So for 3 particles, the state of the systems is specified by the specifying each of this m. So there are 2 to the power n, 2 to the power 3, that is equal to 8 possible states are possible for this particular systems. So if we look now, as it is often that the case in real problem, we have a partial knowledge of the systems that is important to us. So the system can only be in any one of its possible states which is compatible with our knowledge. So states accessible to these systems are described here, that is actually those states which are compatible with all of the knowledge we have about that system. It's important to use all of the information that we have about that particular systems. We have another example, that is actually example 4, where we can also consider 3 spins. So we suppose that we measure the total system energy and we can find is equal to minus mu h. So this additional information limits the states which are accessible to the system clearly. So here we can apply some constraint on that, and then constraint is that out of 8 states, only 3 states are compatible with this knowledge, and this says that the system must be in any one of these 3 states energy, and we can find this particular say. So we can also have applied some constraint on that consider this the arrangement where 2 are up, 1 is down. So we have this 3 arrangement like this. We can also consider a system where we can say that 2 are down, 1 is up. So these 3 are set of such systems, and we have 1 where all are up and we have 1 where all is down, this particular arrangement for that systems. So example 5 is about the systems that is in quantum mechanical 1 dimension, a simple harmonic oscillator with position coordinate x and classical frequency, that is omega. So the quantum energy of this system could be represented as En is equal to h omega n plus 1 over 2 into, so the value of n is equal to 0, 1, 2, 3 up to. So the quantum states of this oscillator are then specified by specifying the quantum number n. So there are essentially an infinite number of such particular states. That is a bit complicated. Coming toward the example number 6, we need to consider a system that has the system is n quantum mechanical 1 dimensional simple harmonic oscillator at position xi with classical frequency of omega I is equal to 1, 2, 3 up to n, and the quantum energy of each particle in these systems could be represented as Ei is equal to h omega I ni plus 1 over 2 into, and ni is equal to 0, 1, 2, 3. So these systems quantum states are specified by specifying the values of each of the quantum number ni. So here these are the essentially an infinite numbers of such particular states. So but there are also large number of these states like what we had checked in example number 3. So this is some in this slide we will basically discuss something about the classical description of a systems, that is this description of the state of a system, many particle systems. So the quantum description is also always correct, but it is often useful and convenient to make the classical description. So how do we specify this state of these classical systems? So that is done by the phase space, that is the space between position and momentum. So we can start with a single particle in 1 dimension. That is the best way because it is very easy for us to do. So classical mechanics can be completely described in terms of its generalized coordinate, that is position, and its generalized momentum, that is p. So we can use for that, and the Hamiltonian formulation for this particular case of classical mechanics, where we talk about generalized coordinates q and generalized momentum p, rather than Lagrangian formulation where we talked of coordinate q and velocity dq divided by dt. So if we look, if we consider a particle that obeys the Newton's second law under the actions of the force on it, so equivalent it obeys the Hamiltonian equation of motions, where we have Q and P completely describe the particle the particle classically, and we given that Q and P at any initial time, say time is equal to t is equal to 0, that can be determined at any other time, that is t, by integrating the equation of motion. Q and P completely describe the particle classically, and given that Q and P at any initial time that is equal to 0 can be determined at any other time t by integrating the Newton's second law equation of motions. So this is forward in time, and that is describing the position and momentum, and that could be completely describe the particles for all time. So this situation can be abstractly represented in a geometrical way, that is actually called as the phase space of any particular systems. Let's come toward the classical phase space, where we have position on horizontal axis and we have momentum on the vertical axis. Q represent the position and P represent the momentum. Keep in mind we have a one-dimensional system, so therefore it's like x and px. If we have three-dimensional system, so correspondingly we will have x, y, z for position, and px, py, and pz for momentum. So this is a two-dimensional space defined by Q and P, that is a classical phase, where we need to at any time t starting at Q and P of the particle, that is describe the state of any particular system. That is done by starting by stating which point in this plane is the particle occupies. Of course, Q and P changes in time according to the equation of motion, so the point representing the particle states moves in the plane of that particular systems. So it's a two-dimensional classical phase space, and we would like to describe the particle states classically in a way that is the number of states is countable. So in order to do this, what you need to do is convenient to subdivide the ranges of Q and P into very small rectangle of sizes, that is del P and into del Q. That is the small patches, and small patches we need to divide that, and we need to consider the two-D phase space that is divided into small cells, and each cell has an area that is equal to h cut, and h cut is by arbitrary very small value to the constants and with the unit of angular momentum. So in this here slide we had divided the phase space into very small patches that we discussed in the previous slides. So in order to describe the state of any particular systems, so this is a particle present in this phase space, and we had divided all this phase space into small patches. And classical particle state is specified by the stating which cell in phase space the Q and P of the particle is in, or by stating that its coordinate lies between Q and Q plus del Q, or its momentum lies between P and P plus del P, where del P is a small increment or change in the value of position momentum, and del Q is the small increment or change in the value of position. So this small state that the phase space cell labeled by the QP, that's the particle occupies in this particular configuration. So if we see the quantum mechanics and the Heisenberg uncertainty principle, then according to the Heisenberg uncertainty principle, it is impossible to simultaneously specify a particle position momentum to greater accuracies. Normally there should always be a type of uncertainty if we simultaneously measure both position and momentum. Say for example, if measuring position at a single time, if we measure separately, it might not have uncertainty, but anyhow simultaneously if we measure, there must be some uncertainty in one of the value. So this is actually called as a Heisenberg uncertainty principle, because we are considering with the very small values or a small position and momentum, that is their quantum level. So the minimum value of h bar naught is 1 over 2 h cut divided by 2, and that has the classical description of a state approaches the quantum description and becomes more and more accurate. So now from that we can realize that many particle systems, one particle in one dimension means we have to deal with a two-dimensional phase space. That was a very simple, or the this possible simple configuration where we have considered one dimensional space where we have a single position and momentum along that particular one dimension. So generalization of to n particle is straightforward, but it requires thinking in terms of very complicated case, because in that case we will have at least three coordinate for the position and three for the momentum. So we will have a type of multi-dimensional phase space where we need to consider the f degree of freedom. So the system is described classically by the f generalized coordinate, that is q1, q2 up till qf, and similarly we also need to consider the same system in terms of f generalized momenta, that is up till p1, p2 up till pf. So that is the generalized description of any particular systems, and then we can describe. So if we consider n particle and in 3 dimensions, so the degree of freedom or the f generalized momentum will be f is equal to 3n. So this is let's think about very abstract in terms of 2f dimensional phase space, so it's become very complicated, and that's regarded the point in the 2f dimensional space of the system. So 2f dimensions phase space is a bit complicated, and that is fqs and fqps, and we need to calculate the value for that, and accordingly we have the differential value for that, that is q1, q2 up till qn, and similarly the same thing what we have in momentum, that is q del p1 del p2 up till q. So for that we have the Gibbs viewpoint and the Boltzmann viewpoint, where something is expressed, and that could be discussed in a separate lecture, where we would like to discuss the viewpoint of Gibbs about this state and viewpoint of Boltzmann about this space and about this 6-dimensional space. So thank you very much for today's lecture.